Otherwise, I think we can go for Dr. Maurice talk from the from the CNRS, and then he provide a talk with a title of towards ergonomically enhanced wearable systems.
Oh, thank you, Myung-Ik, for the nice introduction. Yeah, so I work at CNRS, which is a French research institute in France. And specifically, my lab is located in Nancy, in the east of France. So what we're doing in my team is working on physical human-robot collaboration, which includes both collaborative robots, but also more recently, wearable systems such as exoskeletons. And actually, contrary to what we've heard up to now, we don't really work on rehab or assistance to impaired people, but rather we focus on what is sometimes referred to as human augmentation. So that's basically assistance to healthy people to help, for example, increase the force that you can apply or reduce fatigue. Especially for occupational applications, to try to address the problem of musculoskeletal disorders at work. And in this domain, actually, lately, wearable systems such as exoskeletons have received a lot of attention, and specifically passive exoskeletons. So as it was referred in one of the previous talks, these are unpowered systems that actually works with a force transfer most of the time using springs. And these passive systems have started to be, some of them have started to be commercialized, and some are even starting to be deployed in some factories. And this actually raises a couple of questions. One of them being like, how do we measure and what are the effects of such system on the human user? Because these are wearable systems, so of course they are tightly fit on the user, and they can have many effects, ranging from, of course, like physical and physiological effect on the person, both where the exoskeleton is worn, but also on other part of the bodies. If the exoskeleton is actually changing the way you move. And it goes all the way to effects such as cognitive or psychological effects, because it's just somehow changing your body. So I would like to actually present two studies that we conducted in two different collaborative projects that I was involved in, on the evaluation of two of these passive systems. So just to be clear, this is not systems that we developed in my lab. These are commercial systems that we evaluated in two different conditions. So the first system is the Pixo shoulder exoskeleton that is developed by Ottawa company, which is a partner in the European project Andy, in which we conducted this study. So the Pixo is designed to provide arm support during overhead work. So basically, that's when you work with your arm raised, it's kind of supporting the weight of your arm. And this works thanks to a spring here, which actually generates an upward support torque in the passive shoulder joint there. So to evaluate the system, we conducted a lab study where participants had to perform an overhead pointing task, like you can see on this video. People subjected the experiment both with and without the system, working for about 12 to 15 minutes in both conditions. And we equipped them with a wide range of sensors to evaluate many different effects. And actually what we showed was that so the Pixo shoulder seems to actually reduce energy consumption and metabolic cost during overhead work. And it goes with a reduction of the physical strain on the shoulder, which is kind of expected, of course, because it's what it's designed for. But it is achieved importantly without increasing stress on the low back, or without changing the duration of the motion. So it does not really change, for example, productivity for this task. So these are for the objective measures, but we also wanted to evaluate how the participant perceived the device, because sometimes you can have a mismatch between objective and subjective measures. And in this case, actually, we evaluated both the perceived workload as well as different factors that are part of the acceptance of the system. And this just confirmed what we had seen with objective measures, because participants were mostly positive. But I mean, we still have to be careful there, because this was a college student basically, and not real end users. So this needs to be considered with care. Going beyond this, let's say, experimental evaluation, we complemented the results with a musculoskeletal stimulation using the Anybody software. And in my opinion, this kind of stimulation is very useful and a good complement to the, let's say, maybe ground-truth experimental evaluation, because they can easily provide many measures that you cannot achieve otherwise. Like, for example, I mean, you want to make sure that the exoskeleton is not transferring the problem to any other body parts like muscles or joints. And it's kind of hard to equip a real person with many EMG sensors everywhere. So that's where the simulation is actually a good addition. And when we compared for the measures that we had both for the simulation and experimental evaluation, when we compared the trends for the lab, like for the experimental and simulation study, they were actually quite similar, showing that, I mean, the simulation is quite reliable there. So overall, these are mostly positive effects in terms of, let's say, biomechanics and physiological effects of the PyExo. But what I would like to highlight is we then looked at whether it was changing the way you move or not. So in terms of hand motion, it doesn't really affect the way you move. We still have this very typical profile of reaching motion. But when looking at joint motion, we noticed that the arm is actually much more abducted when you're using the system. So it's much more on the side like that. So what we don't know is whether the exoskeleton is pushing you in this direction or whether it's a deliberate choice, because I mean, arm abduction is actually uncomfortable, and in terms of ergonomics, it's not recommended, because I mean, you have a large gravity effect. You need to support the arm, the weight of your arm. But in this case, the exoskeleton is actually taking care of that. So it might be, it's just an hypothesis, that people, when you don't have to support the arm of your weight, the weight of your arm anymore, maybe you can give a higher priority to other criteria, like maybe you can then raise your arm to have a better posture of the wrist, to have more dexterity, etc. So maybe it changes your priorities in terms of how you decide to move. But that being said, what remains to be studied is whether this arm abduction, this abducted arm posture might still not be recommended in terms of ergonomics, even if you don't have the action of gravity, like for other, let's say, other reasons. So moving on to the second study, this was now with the Levo exoskeleton, which is actually for lumbar support. It's also a passive system. You have springs in the hip that generate a support torque when you are bending forward. And we actually tested it. So it was very preliminary pilot study let's say, during the COVID crisis, to help doctors who have to move patients from their stomach to their back and vice versa. And during this maneuver, the doctor, especially the one who is at the head of the patient, remains bent forward for quite a long time. So it's very fatiguing for the low back. So we tested the system, which is initially developed for logistics, and we evaluated the kinematics, but also we looked at dynamics. And for this, we used again simulation and dynamic simulation. This time, not a musculoskeletal simulation, but rather it's rigid body simulation with a tool that we developed in my team, which enables us to easily estimate the internal joint torque. And I mean, of course, it's way less detailed than simulation, musculoskeletal simulation, but it's much faster because it runs almost real time. So in terms of results, this was just done on 3 doctors, so it's a very small sample. What we saw is there is a small reduction of the lumbar torque and lumbar muscle activity, so it goes in the right direction. But most importantly, we were able to test it in a real ICU, so in a real ICU during the COVID crisis. And we actually showed that it was feasible to use the device, even though there are like kind of very strict hygiene rules. So they could use it. And the doctors who use it for like one shift, they say at the end of the day, they felt less fatigue when using the device. So it's also a good message. Then we left the device in the ICU for a few months so that doctors could use it. And actually the lessons that we learned there, which are more regarding organization, but I think it's important to point out is, first, initially the device was shared between people and it turned out it didn't work because they had to change the tuning all the time and they just don't have time for that. So then we attributed one exoskeleton to one doctor. And what we noticed then was that it really influenced the way the job distribution, who was doing what, because then the colleagues who didn't have exoskeleton said, okay, you have this, you have the assistants, you have the exoskeleton, so you need to go and do the strenuous job, like kind of turning the patient. So I think this is just something that we need to keep in mind when deploying these systems. And finally, very recently, we had been conducted an additional study on the level on a patient bathing task, because it's a task that nurses do very often, where they have to remain bent forward for a long time as well. And this is a lab study with non-expert participants. But here, what we noticed, and which is a little bit similar to what we've seen with the Paexo shoulder, is that using the system seemed to change the way you're moving. And actually, people wearing the level were bending forward much more by about 10 degrees during the task. So it did not really change the muscle activity of the back, abdominal, and leg muscles. And this is probably because people had support from the exoskeleton, so they could bend forward more without extra effort, but still they were changing the way they were moving. And here again, it needs to be investigated further, whether it's a constraint, because maybe you cannot go as close to the bed with the exoskeleton because it's taking some space. But maybe it's just a choice because it's easier for you if you are closer to the patient. But what are the consequences in terms of biomechanics of these changes? It remains to be clarified. So overall, I mean, these passive systems have good potential for postural support, especially for occupational applications. But of course, I mean, they also have strong limitations. If you want to carry some heavy loads, you can't. If you want to adapt the assistance that you're provided to the context, I mean, in that case, you need some active system or at least some adaptive system, which brings the question of how do you control such system in a way that that is intuitive and comfortable for the human to use. And here I would like to talk to go a little bit more towards modern neuroscience and talk about an experiment that is not specific to exoskeletons, but it's in general about wearable human-robot interaction. And this is the question of, if you're interacting physically with the robot, if the robot exhibits some motion patterns that are similar to what a human would do, is it easier for you to interact with the robot? Because if we consider human motions, they are very stereotyped. For example, you might have heard about the minimum jerk motion in reaching movement, and there are others as well. So we actually conducted an experiment in which there was a robotic arm that was moving by itself. And participants had to hold the end effector of the robot and move along with the robot in order to exert as little force as possible on it, which means moving with the robot and anticipating the motion of the robot as well. And so this robot moved according to 4 different velocity profiles. The first one, which we call the biological profile, is according to the 2/3 power law. So when people do drawing motions and curve motion, studies have shown that they exhibit very typical patterns, which is the tangential velocity depends on the radius of curvature of the path. And basically, it is like the straighter the path, the faster you go, which kind of makes sense, but this is very typical. So the robot moved either according to this biological profile, according to a constant, constant tangential velocity, what we call the exaggerated, which is you go even faster in straight lines and even slower when it's curved, and the reverse, which is the opposite. So you accelerate during curved section and you slow down during straight line sections. So the instruction was to exert as little force as possible while still, of course, grabbing the end effector of the robot. So we measure the force, the interaction force in the horizontal plane. And this is our performance metrics. And we actually showed that this force is much smaller, significantly smaller, when the robot is moving according to this biological profile. So, and this was without practice. So basically, if you arrive, you have to interact with the robot, it's easier, it's more natural for you if the robot moves according to motions that you're used to, which kind of makes sense, but still, I mean, it's good to verify it. Now the next question is, okay, this is like, without any training, this is what is easier for you. But can you actually learn a non-biological profile during physical human-robot interaction, which is important because sometimes you don't have the choice of the way the robot is moving. So we conducted an additional experiment where people trained for 2 hours with the constant velocity profile, which is non-biological, but still not crazy either. And some of them trained without visual feedback, some with visual feedback, which was this red line indicating how much force you're exerting. And so it's moving up and down, and you need to try to keep the bar as low as possible. So what we observed was without visual feedback, people could not learn. They did not improve. With visual feedback, all the participants, and this is just a small number, but this is actually confirmed by subsequent studies that is currently ongoing. So all participants with visual feedback were able to improve. So you can learn. But actually, they were able to improve only after 2 hours of practice. Their performance was similar to what they achieved with the biological profile with no practice. So they just came to the lab, do that, and the performance was the same. So I guess the take-home message is you cannot always choose how your robot is moving. Sometimes you have constraint because of the task, etc. But if you could, considering some insights and principles from human motor control could help to, let's say, facilitate the interaction. So to conclude my talk, I think so passive systems have a good potential for several occupational applications, but there are still remaining questions about how they affect the motion, and especially in terms of long-term effects, how does it affect you and your motion and body? And regarding passive systems, which are also active systems, which have like let's say different benefits. In that case, when you're controlling your system, looking at human motor control as well might facilitate the interaction, and so possibly help get a better and easier acceptance of the system by the users. So thank you for your attention, and if you have any questions, I will be happy to answer them.